Hello students, welcome to class. Today we will get started with time series data and time series analysis. I will be introducing some preliminary conceptual ideas before we actually move on to modeling and analysis. This is an exceptionally important topic because often in the real world we are encountered with sequence of data of diverse kind, and in most applications, both engineering and science, we are required to make sense of this data, and often it is difficult because this data visually may not look very structured and organized. It may look very chaotic, very random, but yet hidden underneath this chaos and random looking data, one may be able to unearth certain statistical patterns. And that may shed some light on the underlying phenomena and help us understand the processes involved in a better manner. So what does a time series data look like? Well, symbolically, we could just represent a time series data as a sequence of numbers indexed by their time of appearance. So for example, here I have a set starting with y sub naught, followed by y sub 1, y sub 2, and so on, y sub t, and it could be infinite dimensional, technically speaking. The subscripts here represent the time index at which the particular data was sampled. So if I have to give you an example, you could think about these y sub t's as amount of rainfall in a year, where t may represent the month and y sub t may represent the average monthly rainfall corresponding to that particular month. Or if I have to give you a more technical example, I could talk about Gaussian white noise, something very familiar with statisticians. And it is generally represented by the symbol epsilon sub t, where epsilon sub t is normally sampled from the Gaussian distribution with mean 0 and standard deviation sigma. And these are independent random variables. Now, this white noise is something that will come up a few times later in the subsequent lectures. So since we are talking about it, I must mention the three distinguishing characteristics of white noise. The first two features actually follow automatically from its definition, that being it is normally distributed with mean 0 and variance sigma square. So expected value of epsilon t is 0, which is the mean. And expected value epsilon t square is just the variance, which is sigma square. And of course, there is another important property, which is the expected value of the product of epsilon t and epsilon tau is 0 whenever these indices t and tau are not the same. And this property we will use many times when we talk about time series models. So please keep this in mind. Next, we should also talk about the concept of realizations. And this comes up when we actually perform a statistical experiment. Now let me give you an example. Let us say there are three of us. My name is Amrik. I have my friend Mohan and another friend of mine, Sheila. Each of us are going to perform a very simple coin tossing experiment of a fair coin. And let us say each of us are going to toss the coin 5 times. So the first realization could be a sequence of heads and tails that come up when I toss the coin, right? Could be head, tails, head, head, head. The second realization could come from the experiment performed by my friend Mohan, and he tosses the coin 5 times, which could be another sequence of heads and tails. Let's say it is tail, 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 heads, tail. And the third experiment is performed by our friend Sheila, who also tosses an independent coin, independent of each of our experiments, and she gets a sequence of 5 results: head, tail, head, tail, head. And each of these experiments are performed independently. So these are what constitute the realizations of a multidimensional statistical experiment. The problem that we are interested in addressing here is, how do we construct a random variable from these sequence of data? Well, what we could do is identify one instant of time, let's say the result of the third coin toss for each of us, and represent that by these letters y sub t of superscript 1, which corresponds to the third toss of my experiment, y sub t with subscript 2 that corresponds to the third toss from the experiment conducted by Mohan, and the third entry could be y sub t superscript 3 coming from the experiment performed by Sheila, and so forth. So you could have I realizations likewise, and you could sample the data from a particular time index, in this case be t, and line up all the results of the realizations. That would form a sequence of random numbers, which we call the random variable capital Y sub t. Okay? So it is important to know and understand how to construct a random variable from a given data set of random experiments. Okay? So now that we have defined random variables, we can talk about the moments or the statistical moments of the random variable. And of course, the simplest one is the expected value of the mean, which is denoted by expected value of y sub t. So I haven't written it here again because that's pretty straightforward. The next statistical moment is what is known as the variance, which is represented by this letter or symbol gamma 0t. And that is defined as the expected value of y sub t minus mu sub t whole squared, where mu sub t happens to be the mean of the random variable, or mean of the random sequence of numbers sampled at t. Likewise, we could also define a term called autocovariance, which is represented by the Greek symbol gamma sub jt, and is defined as the expected value of yt minus mu t times y sub t minus j minus mu sub t minus j. So we are trying to find the cross correlation between the random variable at time t and the random variable at another time index, in this case t minus j. And that is what is known as autocovariance. Auto because it is a self-covariance, so to speak, because we are only talking about the random variable of y sub t. We do not have two different random variables. Right? If we did, then we would have what we call the covariance. So if we have two random variables, x and y, the covariance of x and y is given by the expected value of x minus mu x times y minus mu x. Okay. So when we have a time series data, we may be interested in actually analyzing the cross correlation between the random variables or the entries at a certain index, or time instant, and another time instant. We want to see, for example, is there any correlation between the rainfall in the winter months compared to the summer months, for example? So y sub t could represent the average rainfall in the summer month, and so on and so forth, and mu sub t minus j could represent the average rainfall in the winter months. So broadly speaking, this is the idea of autocovariance. Now that we have defined certain useful terms, we are able to define certain phenomena that are relevant to time series data. And in fact, there are two phenomena that we'll talk about in particular in this class. One is that of stationarity, and the other is ergodicity. So what is stationarity? And we'll only restrict our discussion to weak stationarity. There's also something called strong stationarity, but for this particular course, we'll leave that aside and we'll talk about weak stationarity. So whenever we talk about stationarity in this class, think about weak stationarity. So weak stationarity relates to a random sequence of data when the following three properties are satisfied. The first property, the expected value of y sub t, the random variable associated with the random experiment, is equal to mu, is independent of time. Note that I did not use the subscript mu sub t because it is independent of time, it is constant in time. So expected value of y sub t is mu. The autocovariance, gamma jt as defined above, also turns out to be independent of time, so it's a constant, so I'm no more using the variable t, gamma sub j. So that's the second property of stationarity. And the autocovariance function, gamma sub j, is symmetric in its argument, which means gamma sub j is equal to gamma sub minus j, which should be obvious from the definition of autocovariance. So if these three properties are satisfied by a time series data, then we say that that particular phenomena or process is stationary, weakly stationary to be precise. Likewise, we have the concept of ergodicity. We say a time series process is ergodic when time averages of the random entries in the sample can be replaced by the ensemble averages, right? What does that mean? Well, time average is just mean over time, right? So y sub bar is the time average. You sum over all the y sub t of a given realization over t and divide by the total time, which is capital T. If that happens to the expected value of y sub t, which is nothing but the ensemble average, then we say that the process is ergodic. In fact, it need not be equal. Y sub bar need not be equal to expected value of y sub t. It may only approach the ensemble average in the sense of probability, but these are technical terms which you don't really have to bother about in this particular case. But in case anyone's interested, please look up what this approaching in probability sense implies. So broadly speaking, if we have the time average which equates to the ensemble average, then we have an ergodic process. How do we know that that is indeed the case? Well, we can decipher whether the process is ergodic or not based on the autocovariance functions. And in fact, if the autocovariance function gamma sub j happens to approach zero sufficiently fast as j tends to infinity, then we can call the process ergodic. And how do we know that? How do we know that gamma sub j approaches zero sufficiently fast? Well, it turns out by a simple theorem from calculus that if gamma sub j is absolutely summable, which means the summation of absolute value of gamma j running from 0 all the way to infinity happens to converge, then the process is ergodic. And in fact, you should understand and relate yourself with this notion of ergodicity and stationarity, because once we introduce the time series models in the next set of lectures, we will talk about whether those models are ergodic or those models are stationary or not. And this is useful because the stationary process helps us in prediction. An ergodic process helps us in calculation of the moments easily. For example, it may not always be possible to calculate the ensemble average. However, if we have with us the sequence of data, we can easily compute the time average, because we could just sum over the sum over the entries over time, and that will equal to the ensemble average. Ensemble average may be more difficult to compute because we may not know the probability distribution from where the random variable is coming from. And if we don't know the probability distribution, then it becomes extremely difficult to compute the expected value. Because recall, the expected value of any random variable x is nothing but the product of little x's, which are the outcomes of the experiment, times the probability distribution, of course in aggregate form. So if we don't know the probability distribution, calculating expected value of y sub t would be difficult. But if we somehow happen to know whether the process is ergodic or not, let's say for example by analyzing the autocovariance function and checking if they're absolutely summable, then we could say, well, hey, the ensemble averages are nothing but the time averages, and I know how to compute the time averages because I have the data available with me, and that happens to be the expected value of the first moment. So these are extremely useful when doing statistical analysis.